All right, so here we go with this, okay? Acid-base part 2 here. We continue our information on acid bases and we add to it. Now, we've seen this, but we haven't put a formal definition to what I'm about ready to explain here, and that is the common ion effect. What the common ion effect is saying is if we have a weak acid or a weak base and we add a salt, an ionic substance, into our solution, there's going to be that common ion, okay? The bottom line here, it doesn't say this, but the bottom line here is when we have a common ion, we are going to start out, we're going to have initial values of one side of the equation that is not 0. And like I said, we've seen this before. It's one of those problems I had to walk through with you pretty extensively, but we haven't put a name to this, okay? All we have to do when we have a common ion, is we have to solve it just like an equilibrium problem, but our initial concentrations are going to be not all 0. Okay, so we're going to have more than one initial concentration that we have to deal with here. All right. Questions on this? Does anybody need it? All right. So here we go. We have this. We want to know what is the pH of a solution by adding 0.3 moles of acetic acid to 0.3 moles of sodium acetate. Okay. In enough to make a 1 liter solution. So I'm going to start out by saying this. I'm going to start out by saying, hey, we are going to go ahead and we're going to have to get an ice chart. Okay. It's an equilibrium expression. And with this, there's an additional piece of information I want to just start out and give you, and that's the Ka of our particular acetic acid. So acetic acid has a Ka, and this is just looked up from that chart, that is equal to 1.8 times 10 to the negative 5th. Okay, and we'll use that here in a second, but I want to pull out some important information. All right, we're used to saying this. We're used to saying, hey, point something mole of our acid, point something mole of our base, and we write that down as our initial quantity. So with acetic acid, and I want to point out too, I'm going to start using this quite a bit, I have 0.3 moles in 1 liter. So 0.3 divided by 1 is still what? 0.3. So our molarity here is 0.3. And so what that means is we have right now 0.3 molar acetic acid. And I guess we could say 0.30 molar. Okay. Before we said, all right, that's all we have. We're going to make these zeros. But now we have to worry about this. And that is this business on sodium acetate. And I didn't put the formula, but sodium acetate is NaC2H3O2. And it's solid, and we dissolve it in water. And what happens to ions or an ionic compound when we dissolve it in water? Salt, and it breaks into its individual ions. So our individual ions here is Na with a 1 plus, and it's aqueous because we dissolved it in water there. And then it's our, what we call our acetate ion, C2H3O2 minus, and this is also aqueous there. And now let's think about this. If we go back and we look at our equilibrium equation, does Na plus really play a role at all into our equilibrium equation that was printed up there. Is there any Na plus in this equation? No. And so if the answer is no, then we don't really have to worry about it. It's there. There's some of it there, but it's a spectator ion, and it just, again, will not affect the pH. But what we can think about is this. If we have 0.3 moles of this compound, we could do one-to-one stoichiometry. And what that means is that if we have 0.3 moles of sodium acetate, our real important factor here, the acetate ion, means we have 0.3 moles of this stuff here. Now, we take 0.3 and we divide it by 1, and our initial amount here is going to be 0.30 molar. Okay? And I'll ask you this. Do you see anything about H plus or H3O plus given in the problem? We don't. So again, our assumption is if it's not listed, it's 0. But our big new factor is this. A common ion is going to come from a salt that's dissolved in our particular solution. So we have this, and we don't know the change still. And so we would say, okay, well, if we don't know the change, we're typically going to take away from that original substance, that original acid. So we would say minus X, because we don't know the change. And then if we minus on the left, well, yeah, very good. We got to add on the right. Okay, so we add an X on each side, and at equilibrium, we end up with 0.30 molar minus X. We end up with X, and then 0.30 molar plus our X. Okay. Now, at this point in time, I always like to stop and I always like to rewrite my equilibrium expression. And I'm not going to put any numbers, but I'm going to have this. I'm going to have Ka equals our H3O plus times our acetate C2H3O2 with a minus, all divided by our acetic acid there on bottom, or our concentration of acetic acid. And now, once we have this, I want to go ahead and I want to actually start inserting our particular values. Okay, so remember, Ka is given from that chart, and so I'm going to go ahead and I'm going to replace this. I'm going to say 1.8 times 10 to the negative fifth equals our items at equilibrium. Except, do we really want to deal with the plus and minus X? No, because we'd have to use the quadratic. So somebody remind me, what would we have to do to make sure that we can get rid of those?
Multiply the K by 100 and compare it to the initial amount.
Perfect. Now, I'm going to do that in my calculator. Is everyone okay if I don't write it down? All right. So if we multiply our Ka by 100, I take 1.8 times 10 to the negative fifth times 100, and I get 0.0018. Is 0.0018 bigger or smaller than that original amount of 0.3? Smaller. That's good. What that means is that we can assume, and what that means is that this minus and this plus X goes away because the assumption works. Okay, because what Hannah said there of we take Ka times 100, we compare that, it has to be much, much smaller than our original concentration. It does, and that's why we can get rid of those X's. And so here we go at our equilibrium. So at equilibrium, we're going to have x times, since we got rid of the plus x, 0.30, all divided by, again, we got rid of the minus x, the concentration there of 0.30. Now, what do you notice here that we can do to help us out mathematically?
Slice.
Yep, slice it, cancel it, and that means 0.3 is going to cancel out with 0.3, okay? And so when we do this, our x is equal to 1.8 times 10 to the negative fifth. And really, what is x equal to? Yeah. So if we know the concentration of H3O plus, how can we find the pH? Too easy. So we say pH is equal to the negative log of 1.8 times 10 to the negative fifth. And I'm going to report this to 2 decimals here. So negative log 1.8 times 10 to the negative fifth. When I do this, I get a pH of 4.74. So pH equals 4.74. Okay, questions? Quite a bit of work. And so here's what we're going to do. The next few slides here are going to be, how can we reduce this? How can we get rid of some of this redundancy here? Okay. Questions? Anybody need this? All right. So we go through this and we get to this. All right. A buffer. Biology loves to say, hey, this has a buffer, that has a buffer. We use this in our bodily systems. Chemistry side of the house is simply going to be a buffer. Is going to be a solution that resists change in pH. Going to be pretty consistent almost in a lot of circumstances. But it has to have a weak acid and its conjugate base. Okay, you have to have some things present at the very, very get-go. So the thing that we just solved, the problem that we just solved, is a buffer solution because we had some acetic acid, the acid part, which is weak, and then we had that acetate, which is its conjugate base. Now, we could also say the same thing. We could have a little bit of weak base and some of its conjugate acid, and we would just have, instead of using Ka, we would have Kb. All right? Why buffers are so important, or what's happening with the buffers there? The acetic, or the acid, we could use acetic acid, is absorbing some of that OH minus. So it's taking away any base that we might add. The base is absorbing some of that H plus and reacting it, and it's not allowing the pH to change very significantly. Okay? Questions? Anybody need this? All right. So let's see what happens with this. All right. Generic buffer example here. All right. We have the generic acid HX. It breaks off into H plus and X minus. All right. All of these things are aqueous here. And so if I said, hey, let's write the Ka. The Ka here would be equal to what on top? Yep, exactly. Products H plus times Rx minus. All divided by our generic weak acid. Great. Let's go one step further now, and let's go ahead and solve for H plus all by itself. Okay. And so we're going to cross multiply. And so when we cross multiply, we would end up with this. Ka times the concentration of Hx is equal to our H plus times Rx minus. Now, one further step, how would I get H plus all by itself?
Divide by X minus.
Okay. Divide each side by x minus, okay? And so what we would end up is this. We would end up with h plus equals our Ka times our hx all over x minus, okay? And that's great. That gives us a starting point for what we can talk about next. So we solve for H plus because remember, if we know H plus, we can plug it directly into that pH formula, which is great, but we still have to figure out, okay, how exactly do we get to that point there, okay? And so what we do is use this kind of to catapult us to the next portion, okay? So what I'm going to do is I'm going to actually copy this so I don't have to rewrite it, because the next thing that I write is going to be this. Any questions, though, before we move on? So essentially, this allows us to get to a platform to discuss our next point. Yeah.
Why did we change it to H plus?
Good question. Okay, so we want to isolate as much as possible H plus, because if we know H plus and we can throw numbers in and solve it, we can really easily find the pH. So we're trying to reduce the work by getting straight to H plus quicker. Yeah, that's a really good question. Any other questions? All right, so let's keep moving on here. So again, that last part that I wrote down is going to be our starting point for what we have here, okay? It says the pH of a buffer is related to Ka. Well, yeah. It's also related to their relative concentrations. So let's make this formula actually useful, okay? What we're going to do on each side here is we are going to multiply each side by that negative log. So each side is going to be multiplied by negative log. And so on the left-hand side, we're going to end up with this. We're going to end up with negative log equals the concentration of our H plus. Okay, and then this side, all right, I'm going to do a little bit more, and that is this. I'm going to pull out that Ka. Remember, it's our, what we call it, distributive property in math. I'm going to pull out the Ka, and I'm going to start out with just negative log of our Ka. Now, I'm going to keep this, and I'm going to say, hey, times my negative log of my acid over my base. And now we're going to do some thinking. Negative log of H plus could just be equal to what?
pH.
Yeah, the pH, right? So if you don't remember that, the pH is equal to the negative log of our H plus. So instead of having negative log of H plus, let's go ahead and let's insert the pH into this portion here. Okay. Now, the next thing here, you might not exactly remember this, but with our logarithms, we can do a couple of different things. Number one, we have negative log times a negative log. By rules of logarithms, if we go ahead and we say, all right, let's get rid of this negative log of Ka, which, does anybody remember what negative log of Ka is? We talked about it very, very briefly. the negative log of the Ka is equal to this value we called pKa. So instead of using negative log of Ka, we're going to use our pKa times the negative log of our acid over our base. Okay? Now, you'd have to ask the math department here questions on this, but by nature of logarithms, if we have times a negative log, we can rearrange that, and I'm going to rewrite this stuff over here on the right. We could rearrange this to this. pH still equals pKa, but instead of using times the negative log, we can get rid of 1, the multiplication, and 2, we can get rid of the negative sign. If we say plus log, and again, this comes all back to the rules of logarithms. If we do that, though, to flip the sign, we actually have to flip-flop what's on top, what's on bottom. Again, those are logarithm rules. Math department would have much better or clearer answers to why that is. When this happens, we would put the base over the acid, okay? It's all because we are getting rid of that negative log, all right? It makes it a lot easier to put in our calculator. Now, instead of having H's and X's and HX's, we could also just say this. pH is equal to our pKa plus the log of simply our base over our acid. All right? And a couple things here. One, I'm going to box this in. Okay, first thing, you have to have a buffer. Second thing, this is called the Henderson-Hasselbalch equation, and it's going to allow us to look at an equation, and it's going to say, hey, we can plug these numbers in as long as we identify we have a buffer into this formula, and we can calculate our pH. The third thing is this. When I rewrote it, base over acid, you don't have to have the concentration. As long as you have moles of the base and moles of the acid, you can use this formula. So no longer do you have to take the time to actually find molarity and molarity. You can go directly in to this formula because it's just a ratio. Questions? Does anybody need this? All right, so last problem won't take that long because we have this. All right, so we want to know the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate. Okay.
You can find that in your Apple Music library.
Ka is given at 1.4 times 10 to the negative fourth. Now, before I showed you all this, you'd say, hey, I got to get my ice chart. I got to find out what's initial. I got to figure out the change. But if we ask ourselves, is this a buffer? Think, do we have some weak acid and its conjugate base? We do. We do. Initially here, we have 0.12 molar lactic acid. All right, 0.12 molar acid. All right. Now our base comes from this sodium lactate. So again, if I take NaC3H5O3 and it's a solid, I add it to water, it would break down to sodium Na+. Does that really matter? No, it does not really matter. It is aqueous, does not matter as well. And then we would have some lactate. Now, lactate is the conjugate base to lactic acid. Okay? Now, here's my question for you. If we have 0.1 molar sodium lactate, how much lactate ion do we have? Yep. And so if you want to think about this as such, we have 0.1 molar of this business here. We would have 0.1 molar of that business there. All right. So initially, we already know, hey, we have some weak acid and its conjugate base. If you have a weak acid and conjugate base, you can immediately turn to that Henderson-Hasselbalch equation. So we would have pH equals pKa plus the log of what goes on top?
C3H or base.
Yes, you are correct. That would be our base over our acid, okay? Now, base and acid, we can plug these numbers in that we've written down. And so I'm not too worried about that. But our pKa, if we just think about this for a moment, pKa is equal to what?
Negative log of Ka.
Yeah, negative log of Ka. So I'm going to say negative log of this number right here, 1.4 times 10 to the negative fourth, okay? And so if I plug this in my calculator, and I'm going to keep 2 decimals here. I realize significant digits, we should keep only 2 total numbers, but 2 digits is going to get a lot nicer. And so I plug that in my calculator. I get a pKa of 3.85. All right. So now we're in the driver's seat. To find the pH, all we would have to do is say, hey, pH is equal to that pKa value, which we just found at 3.85, plus the log of our base, which one's our base again?
0.1.
Yep, 0.1 molar over our acid. What value is our acid?
0.42.
Yep, 0.12. And so if I do this, all I have to do is say this, 3.85 plus log of 0.1 divided by 0.12, I get a pH of 3.77. Okay? Now, pH does not change very much from the pKa value. And then I want you to think about this. A pH of 3.77, is that smaller or larger than the pKa value of 3.85?
Smaller.
Smaller. So a smaller number on the pH scale, do we get more acidic or more basic? Acidic. Acidic. Think about this. 0.12, our acid, is bigger than 0.10, our base. So it should make sense why all these numbers work out. Questions? All right.